Welcome back, students. In today's lecture, we are going to go over the expectation value, which is the average value of all of the quantum mechanical measurements we would make on a given system. So today we're going to put together the pieces that we began discussing last time and actually get a mathematical way to determine the average value or what we would expect to measure in any given quantum mechanical experiment. The learning goals for today are that we can actually solve mathematically for the expectation value of a quantum mechanical operator. And we'll go over in detail how to do that, and we'll do some of that in class, and we'll have lots of practice with this in the coming weeks. We also want to make sure that we can distinguish between the results of a repeated experiment on the same system or an identically prepared system, because these have some weird quantum mechanical implications that I would assume you guys are somewhat familiar with, but we'll go over with that again today. And we also want to look at this idea that I mentioned in class before about quantum superposition. We're going to look at another experiment that shows this, and this kind of blends in with this the second learning goal here. And this is the explanation we have for why repeated experiments do the things that they do. So last time we left off with a bit of a conflict in terms of our postulates. We have these questions like, how can we operate on an arbitrary function of an operator? If our function is not an eigenvalue, how does it fit into the Schrodinger equation? And when we do, how come we only see the eigenvalues for the operator? Why are those the only things that we measure? And then we actually also might want to know, if I do an experiment, what the heck am I actually going to measure? And today we're going to address those things. And the tool that we're going to use to address those is the fourth quantum mechanical postulate. And this fourth postulate is shown here. So postulate 4 states that if a system in a state described by the wave function psi of x and t, and we were interested in the value of observable A, and we measured that once on each of many identically prepared systems, the average value, which we'll often call the expectation value of all of these measurements, is given by this following expression here. So this expression kind of looks nasty, but what we're going to realize is that for most cases, our wave function is actually going to be normalized. So typically in quantum mechanics, the kind of wave functions we'll encounter will come normalized. And remember, if a wave function is normalized, that means that if we were to integrate that wave function, the square of the magnitude of that wave function over all space, we would get 1 because we have 100% chance to find the particle. Well, it turns out that this denominator here is the integral of the square of the magnitude of the wave function over all space. So for a normalized wave function, this denominator equals 1. And for a non-normalized wave function, this denominator normalizes the wave function. And so for the most part in this class, we'll just treat this denominator as 1, assuming we're working with normalized wave functions. So then what do we do with this postulate? How do we use it to find the average value or the expectation value of a quantum mechanical measurement? And it turns out there's a couple different scenarios. So let's go ahead and look through these scenarios to see what might happen. All right, so to look at these problems and to actually solve this expectation value equation here, we're going to want to remember a couple of things. We're going to want to remember first that our eigenfunctions are orthogonal and also that they're normalized. Remember, our eigenfunctions form an orthonormal set. And so for something to be orthogonal on top here, that means if we were to take one of our eigenfunctions and multiply it by a different eigenfunction and integrate that over all space, we always get 0. That's what it means to say functions are orthogonal. Now, if they're normalized, we just talked about normalization. That means if we were to take the complex conjugate of our wave function, multiply by itself, and integrate that over all space, we get 1. And so these two facts, coming from the fact that our eigenfunctions are orthonormal sets, are going to be very helpful in terms of solving this problem. So we're going to look at 2 different scenarios to try to determine what the expectation value would be. And so in the first scenario, we are going to have our wave function here be an eigenfunction of operator A. And we're going to see what this does to the average value that we measure. So to solve for the expectation value, again, the average value, we need to take our function, take the complex conjugate of that, and then multiply it on our function again after it has been operated on by operator A. So the first thing we want to do is say, well, what happens to our function if we operate on it with operator A? Now, if our function is an eigenfunction of A, which it is, we're setting up for this scenario, then when we operate it on A, we always return the eigenvalue associated with that eigenfunction. That's what it means to be an eigenfunction. So what we'll do is always return some constant, and having that constant be a sub j, because it's the jth constant is associated with our j function here. And we're always going to return that function multiplied by this constant. And this is what will happen if our function is an eigenfunction of our operator A. So then we're going to take this and substitute this in up here in the equation. So this is going to give us that our expectation value, or average value, is simply equal to the integral from negative infinity to positive infinity of the complex conjugate of our eigenfunction of x and t times a sub j, which is a constant, times our function of x and t. From here, we note that our a sub j is simply a constant, which means we can pull this constant out of the integral. So this is, we can write this as a sub j times the integral from negative infinity to positive infinity of psi star j x and t psi of j x and t dx. And now what we can realize is this equation here is our normalization condition. So we have one function, the complex conjugate of that multiplied by itself. We're integrating that over all space. So since our wave function has to be normalized, this equals 1, and our expectation value, our average value of A, is a sub j. So what this tells us is that if our wave function is described by an eigenfunction of the operator, the only value we will ever measure is the eigenvalue associated with that operator, or with that eigenfunction in the operator. So this is pretty great. So for example, we could say if our hydrogen atom was in the 1s orbital, and we're trying to figure out, the total energy of our wave function in the 1s orbital, the only value we're ever going to measure is that energy associated with the 1s orbital. So that's pretty great. Now, what if we have the opposite case? So what if our wave function is not an eigenfunction of our operator A? Then what do we do? Well, we've talked about this before. So recall that if our wave function is not an eigenfunction of the operator, we can build it up based on eigenfunctions of that operator. So if our wave function of x and t is not an eigenfunction of operator A, we can always represent it as the sum of eigenfunctions of operator A. And so we'll write that in the following way. So our wave function is actually the sum of from over n from Bn, and then our phi here is going to be specifically our eigenfunctions. So what this is saying is that there is some way in which we can represent this function that is not an eigenfunction of operator A by summing up all of the functions that are eigenfunctions of operator A. And we're going to have a condition here. So our Bn's here are kind of like proportionality constants. So the sum of the square of the magnitude of these Bm's has to equal 1. And what we're doing here is we're like adding together these different functions to make our total normalized function. So this is another normalization condition that will ensure our wave function is still normalized when we sum it from all these eigenfunctions. And now that we have this, we want to operate on this function with operator A and figure out what the expectation value is. So what happens when we operate on this equation here with operator A? Well, if we operated on it with A, so we're operating with A on the sum of all of these eigenfunctions. Right, and so this term, we could write it out as something like B1, V1 plus B2, V2, right? That's what it means to be a sum there. So if we're operating on this sum with our operator, well, that's simply going to return each of these terms here multiplied by the observable that's associated with it. So operating on this function here with operator A is going to return to us an, bn, vn of x and t. And that's simply, right, that's how we're going to do these operations. We're operating on a whole bunch of different terms, and each term will operate as if it was operated by itself. So if we're operating on eigenfunction 1, we return eigenvalue 1. If we're operating on eigenfunction 2, we return eigenvalue 2. And if we're operating on eigenfunction n, we return eigenvalue n. So for us then, that means that our expectation value, right, we'll go back up here. So our expectation value is equal to the complex conjugate of that function times what we've just done here after operating on that function with our operator. So our expectation value is going to be the integral from negative infinity to infinity times, and we'll split this up here. So our function, remember, we're representing as the sum over m, and we're changing the index here because we're going to have m's and n's. So we have b star m of x and t. And then our new function after we've operated on it with our operator a is a sum over n of an, bn, vn of x and t. So here we have this function that looks pretty nasty, if I do say so myself. But lucky for us, we can simplify this drastically. So the first thing I'm going to do is probably not going to look like too much of a simplification, but then we'll evaluate what it means. So I'm going to rewrite this. I'm going to pull the constants and the sums out of this integral, and we're going to get the following. We'll get that this is equal to the sum from m equals 1 to infinity times the sum over n equals 1 to infinity of bm star bn an times the integral from negative infinity to infinity of phi star m of x and t times phi n of x and t dx. All right, so again, we're still not looking super good. It still looks pretty nasty and horrible. But it turns out that it actually simplifies into something very, very easy. Now, how can we do that? Well, we recognize that what are we doing with this integral? We're summing this from m equals 1 and n equals 1 to however far we need to go. And what's going to happen if we do that? Well, we're going to get all of the various combinations. So our combinations here, we're going to end up getting something like the integral of, phi1 star phi1, and then we're going to get the integral of phi1 star phi2, and then we're going to get the integral of phi1 star phi3, and we're going to keep going, and eventually we'll end up, we're back at infinity. We'll end up with phi2 star phi1, phi2 star phi2, and so forth. So we're going to get all of these various integrals. Now, using our properties that we discussed at the beginning of that our eigenfunctions are an orthonormal set, we can see that we simplify these. So since our functions are normalized, the integral of this guy here and also this guy here, so if they're ever the same, that these integrals always equal 1. And so for all of the times that our m and n have the same number, we end up with integrals equal to 1. So those integrals go away. The other thing we have is the rest of these guys, since our eigenfunctions are normalized, anytime that these integrals are not the same number, these whole integrals equal 0. And so that greatly simplifies our math here. So that removes both indices, because if the indices are different, if m and n are not the same, the integral equals 0 and that whole term doesn't add in. And then if they are the same, the whole integral ends up being equal to 1. So what we can do then is simply say that the expectation value is the sum from m equals 1 to infinity of am bm star bm, because the indices are the same and the integrals equal 1. And we can write this here as follows, recognizing that bm star bm is the square of the magnitude of this constant bm. And this is our expectation value. So what is this? This tells us that the only values that we're ever going to measure are the eigenfunctions of the operator. That goes back to postulate 3. So here we can see the origins of postulate 3. And it's impossible for us to measure any value when we operate with operator A that is not an eigenfunction of operator A. Now, what are we actually going to do? How likely are we actually going to measure that? It is determined here by this bm constant. So the square of the magnitude of our constant bm determines how likely it is for us to measure each constant. So if we were to go back and look at the equation that's up on the slide, we have a wave function that is described by the square root of 11 over 4 phi1 of x plus 1 over 4 phi2 of x plus 1 over 2 phi3 of x. If this completely describes our wave function, then we can use this postulate to address, how do we go about this? And so we might want to know a couple things. We might want to say, what energies are we capable of measuring? And if this completely describes our wave function, we are only capable of measuring energy 1, energy 2, and energy 3. So the energy values associated with these 3 operators. Now, depending on the problem, these will be different. So for example, if we were talking about the hydrogen atom, we have the relationship. So we know that En is equal to negative mass of the electron, fundamental charge to the 4th, over 8 epsilon naught squared, h squared, n squared. So this would determine what E1, E2, and E3 are based on this value here. And it'll be different for every problem we do. And then we might want to know, well, what's our expectation value? So that would be the average energy. And we could also ask us a very similar question as how likely are we to measure each of these values? And that is simply the square of these constants here. So how likely are we to measure energy 1? Well, that is going to be the square of the square root 11 over 4, which is 11/16. In the same way, we could say how likely are we to measure energy 2? That's going to be 1/16. And then how likely are we to measure energy 3? It's going to be 1/4, which I'll write as 4/16. So we can show that this number adds up to 1. So this is how likely we are to measure each of these values. And then the average energy is simply going to be the sum of these values. So it's the weighted average. So our average energy in this case is going to be 11 times E1 plus E2 plus 4 times E3 divided by 16. So it's a weighted average of these 3 energy values, reflecting that we are more likely to measure energy 1 than energy 3, and then energy 2 is least likely of all. So using this, we can identify the average energy, the expectation value of energy. So if we go back to the slides, again, we can see just the same sorts of thing that I was writing on the board there. So now we're going to address probably the weirdest thing about quantum mechanics. So the 4th postulate here predicts the average value of many measurements on identically prepared systems. However, there is no way to know which result will be observed in any given measurement. So if we were to measure this system here, we know that 11 out of 16 times we are going to get E1. But if we were to do a measurement, we could not be sure whether or not we are going to get E1 because we have this probabilistic value. So this is very much like rolling a die or flipping a coin. You don't know what you're going to get when you roll the die or flip the coin. Now, perhaps an even more disturbing fact comes when we look at what happens when we repeat the experiment on the same system. So in our normal experience, right, you take a 6-sided die, you roll it, you have a 1/6 chance of rolling any of those numbers. You pick it up, you roll it again, a 1/6 chance to roll any of those numbers. And quantum mechanics works like that if we start on identically prepared systems. If we start on the same system, so after we make one measurement, repeated measurements always return the exact same result as the first experiment. So again, in this example, if I were to measure E2 on an experiment, and I were to take that exact same system and measure it again, I would get E2. Doesn't matter that it's only 1/16 chance. Every single time I measured, I would get E2. And we can see that looking at this following experiment here. So identically prepared systems give different values, but the same repeated measurements in the same system always give the same value. And this, I think, can be very hard to swallow and wrap our minds around. The quantum mechanical explanation for this is that before you do a measurement, the system exists as what we're going to call, and I mentioned this before, and we'll see this on the next slide, is it exists in a superposition wave function. And an example of that is shown here. Again, this is talking about the hydrogen atom. So this shows us that our wave function for our hydrogen atom is described as there's some 1s character, there's 2s character, there's 2px character, there's 3s character, and they're weighted with these different constants here. And so before we do a measurement, our wave function is in this superposition where we can get any value. After we do the measurement, we only see the same value. If we go back to the work we did on the board, we would see that if we're getting the same value over and over again, that means our wave function is just an eigenfunction of the operator. So something about measuring this superposition wave function converts it into just a single eigenfunction of the operator. And now when we do measurements, we only are able to get that value. So doing this measurement, doing this experiment appears to actually change the wave function. It's no longer a superposition and is now just a single wave function. It's collapsed in onto itself. So you might be a little bit skeptical of this claim and find it hard to understand. And we'll look at one experiment to show again that this seems to be the way that our world works. So I have this picture. I assume you guys have seen a picture like this before. This is kind of a silly example of quantum superposition, you could say, where this picture is either a picture of a young woman or an old woman. And it can be kind of hard to see the other once you've seen it. So before you look at it, it exists as both old and young woman. And now for me right now, I'm kind of stuck seeing the old woman, although since I know what the young woman looks like, I can see that as well, but it's hard for me to unsee the old woman there. Okay, so the actual experiment that shows us this idea is as follows. I couldn't find a really good picture of it. There's one in the textbook, but the textbook online is a newer edition that doesn't have this figure. So I would refer to section 14.6 of your textbook for a better figure than this. So this experiment uses polarization beam splitters. And you may be somewhat familiar with this, but you can polarize light if you have the right kind of filter. So sunglasses oftentimes polarize light to restrict the amount of sunlight that gets in them to darken them. And this beam splitter is a similar thing. So when we shine light at this polarization beam splitter, two things happen. If the light is vertically polarized, it can pass through the beam splitter. If it's horizontally polarized, it's going to be reflected by the beam splitter. And so if we were to shine light of random orientation at this beam splitter and then check it over here, we would say, okay, now we have our vertically polarized light. If we check it up here, we have horizontally polarized light. Then what's going to happen is we're going to hit them with more mirrors and pass them through a second beam splitter. And so again, if we're following the light, it's going to be mixed. It hits this. If it passes through, it's vertical, 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 bounces, vertical, 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 still passes through, and vertical, vertical, vertical. We can detect it. And the same thing here, it would be mixed, horizontal, 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 and then it would bounce back again and be horizontal. So what a normal sane person would expect for this experiment is that light that comes in through this system of filters would be either horizontally or vertically polarized. So the vertically polarized light would pass through both filters. The horizontally polarized light would bounce back on both filters. And we would see light that's either horizontally or vertically polarized. In fact, what we see is that the light is mixed. So it's not either horizontally or vertically polarized. It actually has the same random orientation as when it was put into the experiment. So if we just observe out here, we see that the light does not appear to have been bounced or passed through. It rather appears to have been both bounced and passed through and then merged back into its original source material. So again, this is a very strange idea that begins to show us some experimental reasons to believe in this quantum superposition thing. In other words, you could write wave functions that say it's, horizontal and vertical. If we were to measure it in this region after we've done one experiment, we would show that it either is horizontal or vertical, and then it would be stuck that way. But since we don't measure it at all until the end, we see that it retains its both of its components, both of its horizontal and vertical components. Again, pretty hard to understand, and I'll be happy to go over this again in more detail in class. Lastly, we want to discuss the time evolution of a quantum mechanical system. This is our fifth postulate. Again, we're not really going to focus too much on time dependence here, but the fifth postulate states that the evolution in time of a quantum mechanical system is governed by the time-dependent Schrodinger equation, and that is shown as follows. This gives us an expression for the total energy of a wave function and how that interacts with time. And so this function is deterministic in nature, which is what we expect. So that means once you have a particle, it does something predictable as a function of time, like dropping an object in a gravitational field. But again, this only applies in the absence of a measurement. If you do a measurement, that's going to change the wave function. And again, we're mostly going to consider functions that do not depend on time, and our focus will be on the time-independent Schrodinger equation and the first four wave functions. All right. So I want to conclude here with the following notes, again, summing up the last two lectures. The square of the magnitude of a quantum mechanical wave function represents the probability of finding that particle within a certain interval. And this idea, this first postulate, puts restrictions on acceptable wave functions as they have to have meaningful probabilities over the interval that we're interested in. Once we have a wave function and we do an experiment on it, the only thing we can actually observe are eigenfunctions, or eigenvalues rather, corresponding to the eigenfunctions of that operator. And we get these values based on probabilities that describe how the wave function is built up of these eigenfunctions. And again, the weirdest thing that we've talked about is that when we do these measurements on experiments, we actually collapse the wave function and change the experiment. And the experiment changes the wave function. So with that, I will let you guys go. We'll pick up on Monday with the particle in a box model. So we're going to take these ideas and actually apply them to our first quantum mechanical system. We choose the particle in the box because it's relatively easy to understand. And then after that, we're going to move to more realistic models that talk about degrees of freedom like vibration and rotation.